So today we're going to focus on solutions. And what we really want to do is we want to review what solutions are. We want to further our definition of solutions so we can differentiate between them. We'll talk about different examples of solutions. Then we'll also talk about the actual process of forming a solution and also some of the energetics behind it. So we have the solute, which is being dissolved, and the solvent, which is doing the dissolving. So one of the things we typically do with solutions is find the molarity. So recall that molarity, capital M, is equal to our moles of solute over the volume of our solution. And the solution is the combination of the solute or solutes and the solvent. So this will end up having units of moles per liter. Your volume has to be in liters, but we'll typically denote this just with a capital M for molarity. So as we start to look at solutions, there's several different types that we can have. We can have a saturated solution, and you may have heard of something being saturated before. This just means that it contains the maximum amount of solute that can be dissolved in the solvent. So one of the things we'll explore later, but this also means that you have to have solid that is undissolved. And this will be for a saturated solution. An unsaturated solution, this is whenever you can keep adding more solute and it will keep dissolving. There's also such a thing as a supersaturated solution. And with a supersaturated solution, there's more solute dissolved than in a saturated solution, or what would be expected. And we'll look at what that means on a solubility curve. And then finally, we've been talking about forming solutions whenever a solid is being dissolved in a liquid, but you can also go the other way. And that means you could actually have something crystallize out. So this is whenever that dissolved solute comes out of solution and forms crystals. So whenever we think of solutions, we're kind of biased in what we're thinking of. We're always thinking about solids or liquids being dissolved in a liquid. But wait, there's more. So what we can see is that it's more than just solid or liquids dissolved in liquids. You can have any combination of the three phases of matter that we're focusing on in this class. You can have gas and gas, liquids and liquids, solids and solids, and there's examples of all of these. What we're going to tend to focus on would be solid and liquids, liquids and liquids. We may talk about gases and gases, but we'll kind of look at gases and liquids and the effect that temperature has on their solubility. But here's a list of some examples of these different types of solutions. So let's go ahead and start to look at some more of the energetics behind this process. So what I want you guys to recall is, remember we talked about the gas laws previously. We looked at kinetic molecular theory, and we made the assumption that the gases do not interact with each other. They can physically collide with each other, but they're not interacting. But whenever we start to consider the condensed phases, such as solid or liquid, we start to have intermolecular forces. Okay, so if the intermolecular forces are prevalent, let's start to think about this process of forming a solution. So a solution is made up of two things. We have, in our solution, we have our solvent, and we're mixing that with our solute. So whenever this mixing starts to occur, we have to think about the types of intermolecular forces that we have to overcome and the types of intermolecular forces that will result in the solution. So the first example, let's consider maybe we have H2O and ethanol. So in H2O and ethanol, let's say that H2O is our solvent. So we have intermolecular forces between water molecules, so H2O to H2O. And I trust that you guys can identify the types of intermolecular forces, dispersion and hydrogen bonding here, because there's that OH. Same thing with solute. We could have our ethanol with other ethanol molecules. And then finally, once we mix these, now we can have a solvent. solute interaction. And this could also be applied similarly to if you were to mix your solvent of water and sodium chloride. So you can think about, again, the solvent-solvent interaction would be a water-water interaction. Solute, you would have an interaction between the sodium ions and the chloride ions with each other. And then once they start to dissolve, we'll have an interaction between that water and the sodium ions once it's dissolved, and the water and the chloride ions. And we'll start to expand on this like dissolves like. We know that polar molecules will dissolve other polar molecules, and also ionic compounds as well, whereas nonpolar solutions will dissolve nonpolar. One of the new things that we're going to look at would be something that is miscible. And whenever we say that something is miscible, it means that it's completely soluble regardless of the proportion. So an example of this would be what we looked at above. H2O and ethanol. No matter what ratio you try to combine these in, they will always dissolve completely with each other. Whereas if we look at the other example, where we mixed water and salt, you would actually end up with a saturated solution. So there comes a point where no more sodium chloride can be dissolved in the water. So I think it's more intuitive to think about how two liquids could dissolve in each other, how they could be soluble with each other. But how can an ionic compound actually dissolve? Well, let's go ahead and look at that process of dissolution. So what we're going to look at here is we have this nice lattice structure here of sodium chloride, this highly organized solid, and then we have our solvent, so water molecules that are coming through. So what happens is whenever you put the salt into the water, whether you have the cation or the anion exposed, so here we have the anion exposed, what we'll see is the water molecules come by, and that partial positive charge on the hydrogen is attracted, and so that ion becomes what we call solvated. It's surrounded by solvent, and then it breaks off eventually, and then it exposes the next ion. And then maybe that's the cation. Then all those partial negative charges on the oxygen start to come in, and it solvates that ion. And this happens very, very quickly. So we'll see if you put a small amount of salt in water, it dissolves more or less immediately. So this is what the process of dissolving looks like whenever you're forming a solution. But what's actually happening energetically? So what we want to look at is different types of intermolecular forces that we are overcoming, and then different types of intermolecular forces that are now being introduced. So for instance, we have a solvent-solvent interaction. So we're going to require a certain amount of energy to overcome this. So we're disrupting this. So this costs energy, okay? The same thing with solute-solute, whether you have some sort of lattice with like sodium chloride, or you have another solute that's a liquid and they're interacting with each other. You have some sort of intermolecular force, and what we're going to see is we have to also disrupt this intermolecular force. And then we aren't going to focus on this as much right now, but in ionic solids, we actually call this the lattice energy, and that's the energy that's absorbed to overcome that lattice that's being held together. So then what we end up getting is, once we mix these, is instead of disruption, finally we have some sort of attraction between the solvent and the solute. And this is the energy that's released, so it doesn't cost, now we're releasing energy when the solvent molecules start to form around the solute particles and solvate them. So there's one of two ways that this can go. One way is whenever the delta H3, the solvent-solute, that interaction is stronger than the sum of solvent-solvent and solute-solute. So you're releasing more energy than what it costs. And that means that it's going to be an exothermic reaction. All right. So you could also have a case where delta H sub 3, so the solvent solute is actually less than so the energy that's released is less than the cost that it takes to break these up. So this would be an endothermic reaction. So you could think about it like this. You start out with solvent, and then solute interactions. And then we're going to form solvent-solute interactions. If this is stronger, it's going to be exothermic. But if these two processes here, disrupting the solvent-solvent and solute-solute interaction, if this costs more energy, then it's going to be endothermic. So if it costs more energy, it's going to be endothermic. So what's the point here? How does this actually apply in the real world? Well, this is just a little sneak preview to thermodynamics, which is a really big deal. We're not going to go into any of the details of this. In this class, I'm just going to give you a really, really brief overview. So whenever we talk about thermodynamics, what we're talking about is a process spontaneous? And we're not talking about does it happen immediately. We're just saying, is this reaction going to proceed spontaneous, or does it take some sort of external kick? So we can actually figure that out using this equation. Delta G is equal to delta H minus T delta S. So we already know what delta H is. Delta H is the enthalpy. Delta G is what we call Gibbs free energy. T's temperature. And then delta S is this term that we call the entropy. So what actually governs whether or not a reaction is spontaneous or not is delta G. So for instance, if delta G is negative for the dissolving process, it is spontaneous and the substance dissolves. If delta G is positive, the process is not spontaneous and the substance does not dissolve. So the big takeaway here is that delta G determines spontaneity. So let's go ahead and look just a little bit closer at this and then we'll be done. So whenever we look at energy changes, again, this is the reaction. Delta G is equal to delta H minus T delta S. We've had plenty of experience with delta H whenever we talked about thermochemistry. So if we're trying to get this piece, delta G, to be negative, there's a couple of different scenarios that could occur. So delta H, we know there's two possibilities for this. We could end up with delta H being an endothermic reaction, where delta H is positive. Or it could be an exothermic reaction, so if heat's released, and this means that delta H is negative. So then there's this other term, delta S. So delta S is the entropy. And what we're going to define the entropy as, just for us, is we're just going to say that delta S corresponds to the randomness of the system, or the amount of disorder. So what I'd like to consider is, let's look at the dissolving process. Let's say that we have a highly organized solid. So we have some sort of organized crystal structure here. And then we have our liquid where the molecules are just not as organized and they're just kind of freely floating around, they're interacting with each other. So in this case, what we're going to look at is if the solution is formed, so if the solid is dissolved, we may end up with something that looks like this. And what we can see is we went from a highly organized solid and then a liquid that was interacting with itself, and now we have this much more random solution. Okay, so what I want to do really quick is I want to think about a couple of different scenarios. So what happens if delta H is positive? How can delta G be negative? Well, even if the process is endothermic, which means that delta H is positive, this reaction could still be spontaneous. If there's enough disorder in the products. Okay, the other case would be, what happens if you're going the other way here? Let's say we're going from more randomness to less randomness. So we could say that even if the process is becoming more ordered, then if delta H is negative, so it's exothermic and it's large enough, the process could still be spontaneous. If you go on to take a class that you cover more thermodynamics in depth, we would start to explore the effect that temperature has on this. But for right now, if you have an exothermic reaction, so delta H is negative, and you have delta S that is positive, you're guaranteed to have a spontaneous reaction. So we're going to go ahead and wrap up our discussion on solutions with that.